Here we have a question which discusses topics under chapter 9, waves AHL. Let's have a look at the question. A longitudinal wave travels in a medium with a speed v equal to 340 meter per second. So here we have the speed v equal to 340 meter per second. The graph shows the variation with time t of the displacement x of a particle p in the medium. So here we have the displacement x on the y-axis and time t in milliseconds on the x-axis. Positive displacements correspond to displacements to the right. In other words, here the displacements have positive values, which corresponds to displacement to the right, and these negative values of displacement correspond to displacements to the left for the particle p. Calculate the wavelength of the wave. Here from the question, we can calculate the time period of a wave, which is the time taken for one oscillation or one vibration or one cycle. Also the time taken for covering a distance of one wavelength as exactly the distance from one peak to another or from one crest to another. Here we notice that the value is 4 milliseconds. So we have time period t as 4 milliseconds. The standard formula that we know, that is velocity v is equal to displacement x by time t, transforms in wave motion as wavelength lambda divided by time period capital T. So this also refers to or translates to the standard equation that we know of, that is v is equal to lambda into f, where f, the frequency, is 1 by time period. Substituting the value of speed v as 340 meter per second and time period t as 4 millisecond, we get to rewrite the equation in terms of lambda as lambda is equal to v into t. V is substituted as 340 and t as 4. Milli is a prefix which can be abbreviated to 10 power minus 3. So this gives us the wavelength value to be approximately 1.36, which is again approximated using significant figures as 1.4 meter. Moving on to the next part. Determine for the particle the magnitude of acceleration at time t equals 2 milliseconds. So here we notice that the particle's displacement graph is a cosine graph. In other words, its displacement keeps shifting between an equilibrium position to the right and to the left at regular intervals. This is a classic example of simple harmonic motion. And since the body is now adjudged to be in simple harmonic motion, we have the relationship between acceleration and displacement as acceleration A magnitude wise is equal to omega square x, where omega is its angular frequency and x is its displacement. We notice that at time t equals 2 millisecond, the displacement is exactly this value, which is 6 into 10 to the power of minus 6 meters. Omega can be found out since we know time period. The relationship between omega and frequency is omega is equal to 2 pi frequency. And since frequency is 1 by time period, it can also be deduced that omega is equal to 2 pi divided by time period capital T. Substituting, we have 2 times pi divided by the value of time period, 4 into 10 to the power of minus 3, the whole square, times the displacement at 2 milliseconds, which is found out to be 6 into 10 to the power of minus 6 meter. Simplifying this further, we get the value of acceleration to be approximately 1.57 into 10 to the power of 3 meter per second square. Moving on to part C of the question. Another wave travels in the medium. The graph shows the variation with time t for the displacement of each wave at position P. So wave 1, let's assume that is wave y, which is a cosine graph. Y is equal to cos omega t. Wave 2, since it starts from 0, could be assumed as a sine graph. Y is equal to sine omega t. I know sine can be written as cosine, or cosine can be written. Cosine can be written as sine of 90 plus theta sine of omega t plus 90 degrees. So the first wave y1 is sine of omega t plus 90, whereas the second wave y2 is just sine of omega t. Thus, when they ask us to calculate the phase difference, it is evident that the phase difference is the additional value of 90 degrees, or written in terms of radians as pi over 2 radian. This is the value of the phase difference. Moving on, we also need to find out a time at which displacement P is 0. The time instant at which the displacement P is 0 can be observed from the graph to be exactly at 1.5 millisecond. Moving on to the next part, estimate the amplitude of the resultant wave. The amplitude of the resultant wave from the graph is found out to be 4 micrometer plus another 4 micrometer, which adds up to 8 micrometer. So this is the amplitude, or the highest point on the y-axis for the resultant wave. Moving ahead, the next part states as follows. A standing sound wave is established in a tube that is closed at one end and open at the other end. The period of the wave is t. The diagram represents the standing wave at t equal to 0 and t is equal to the total time period divided by 8. The wavelength of the wave is 1.2 meter. Positive displacement means displacement to the right. So here we have a standing wave pattern being followed or formed on a tube that is closed at one end and open at the other end. We know how to measure wavelength. A wavelength is one complete oscillation of a wave, which is measured from the starting to the ending of a wave as such. This constitutes one complete wavelength, lambda, and the pattern formed, or the standing wave pattern formed, confirms that the length covered here for the tube, L, is exactly equal to 3/4 of a wavelength. Since the length is equal to 3/4 of a wavelength, as evident from the standing wave pattern being formed, and the wavelength is 1.2 meter, we know that L is equal to 3/4 of 1.2 meter, which gives the value of L to be 0.9 meter. Moving on, a particle in the tube has its equilibrium position at the open end of the tube. State and explain the direction of the velocity of this particle at time t equal to t by 8. At time t equal to t by 8, we notice that the displacement is a decreasing negative value. In other words, it's an increasing positive value, which means the displacement is to the right, as the statement in the question says positive displacements mean displacement to the right. We know from this statement that the displacement of the particle, or the direction of velocity, is to the right. Moving on to the last part, we are asked to draw on the diagram the standing wave that is formed at time t equal to t by 4. At time t equal to 0, we have the standing wave pattern formed. At time t equal to t by 8, we know that the amplitude has exactly reduced in half. At time t equal to t by 4, which is again twice of the time shown, we notice that the graph will follow such a pattern. The standing wave pattern form will be a horizontal line that is drawn along the equilibrium position. This is the standing wave that is formed at t equal to t by 4. Furthermore, at t equal to t by 2, we notice that the pattern formed is exactly mirror of what is formed before. And at time t equal to capital T, the standing wave pattern formed will be exactly as such. This concludes the solution to the entire question.